So here let me explain how to represent planes or surface in the Cartesian coordinate system. So here consider coordinate axis. Yeah. So this is the origin. Okay. So here, a plane is constructed with the help of x-axis and y-axis. Okay. So this plane is called xy plane. XY plane, because one side is along x-axis, another side is along y-axis, or two sides are constructed with x coordinate and y coordinate. So it is called as xy plane. Okay. And if you observe this one, where this xy plane is located exactly. Okay. So for that, you just see here. So here, where this xy plane is present on the z-axis. So this xy plane is present exactly at the middle of the z-axis, at the middle of or in between positive z and negative z. So here it is. Okay. So this xy plane is present exactly at z is equal to 0. That's why this plane is also called as z is equal to 0 plane. Z is equal to 0 plane. Or there is another reason why this plane is called as z is equal to 0 plane. Okay. So we consider any point on this plane. You consider any point on this plane. So this point makes some distance along x-axis. Consider x coordinate. Okay. It makes some distance along y-axis. Consider y coordinate. Okay. So this point is located at z is equal to 0. Exactly at z is equal to 0. Okay. That's why this point is some length along x-axis, some length along y-axis, and z coordinate is 0. So similarly, if you consider any point on this plane, at every point on this plane, z coordinate is 0. That's why the plane is called as z is equal to 0 plane. Okay. So now we say that what is meant by z is equal to 0 plane means the plane on which at every point z coordinate is 0 is called as z is equal to 0 plane. Or we say that the plane which is located exactly at the z is equal to 0 coordinate is called as z is equal to 0 plane. Okay. Similarly, you consider one more plane here. So whenever you move this plane some distance in vertically upward direction. Okay. So move this plane some 5 units vertically upward direction. Okay. Then you can observe this plane. Yeah. So initially it is at z is equal to 0. If we move this plane vertically upwards 5 units, then it will touch the z-axis at 5. Okay. So that's why this plane is called as z is equal to 5 plane. The plane which cut the z-axis at 5 is z is equal to 5 plane. Or you can say that what is the point on this plane? If you consider any point on this plane, okay, so it makes some distance along x-axis and some distance along y-axis, and it is located at z is equal to 5. So the plane on which at every point z coordinate is 5 is called as z is equal to 5 plane. Okay. Similarly, let us move this z is equal to 0 plane downward direction or along the negative z direction. Okay. So move this plane 2 units downward direction. Okay. So then if you move 2 units downward direction, then it will move and it will move along the negative z axis, and cut the negative z axis at -2. Okay. So this plane is called as z is equal to -2 plane. Okay. The plane which cut the z axis, at -2 is called as z is equal to -2 plane. Or you may consider any point on this plane will be in the form of x, y, -2. Okay. So the plane on which at every point z coordinate is -2 is called as z is equal to -2 plane. Okay. Like this we can define infinite number of planes. So all these planes are combined called as z is equal to some constant. Z is equal to constant planes. Okay, all these planes are combinedly called as z is equal to constant planes. Yeah. So like this, infinite number of z is equal to constant planes are available here. So for example, if you see, all these planes are parallel to which plane? All these planes are parallel to xy plane. Okay. So these planes are parallel to xy plane. And all these planes are perpendicular to which axis? Here you can observe the planes are perpendicular to z axis. Okay. Everywhere, each and every, all these parallel planes are perpendicular to z axis. So we say that z is equal to constant planes are perpendicular to z axis. Okay. So that means if you observe this, what is z is equal to constant plane means the planes which are parallel to xy plane and perpendicular to z axis is called as z is equal to constant planes. Okay. Now, whenever we study about planes, we need to understand one more important point called as a differential surface element. Consider differential surface element. So, which is denoted with ds bar. ds bar. Okay. Actually, what is a differential surface element means? So, differential surface element indicates how the area of the surface is constructed. Area of the surface into direction of the surface. Okay. So, here I have used the term called as a differential. Differential indicates infinitesimally small or very small is called as a differential. Okay. So, here just see the diagram. In this diagram, let us consider any small element or differential element on any one of these z is equal to constant plane. Okay. So, if you choose any small element or a differential element on this plane, one side length is constructed with x, this differential length is denoted with dx. Another side length is constructed parallel to y axis. This differential length is called as dy. Okay. Then what is the area of the surface? What is the area of the surface? So, one side is a differential length dx, another side is a differential length dy. So, the area is nothing but dx into dy. Dx into dy. And what is the direction of the surface? Actually, this surface area is showing which direction? This surface area is showing vertically upward direction and also it is showing vertically downward direction. Okay. So, this vertically upward direction is z axis or plus az cap direction. This downward direction is nothing but negative z direction, that is minus az cap direction. Okay. So, the area of this differential surface is dx dy and this area is showing the direction az cap or minus az cap. Okay. So, I am going to write here the direction is plus or minus az cap. Okay. So, finally, I conclude here the differential surface element for z is equal to constant planes is given by plus or minus dx dy into az cap. This is the differential surface element. Actually, why we need to understand this differential surface element means actually what is the significance of this element means whenever you want to perform surface integral of any vector dot ds bar. Okay. So, that means in the surface integral we need a differential surface element. So, if this plane you are performing performing integration along the z is equal to constant plane or along xy plane, then this ds bar must be substituted with this one. Okay. So, plus or minus dx dy az cap. Okay. So, differential surface elements we are going to use while we are performing surface integral. Okay. So, this is the one kind of one combination of planes or surface. Okay, let us see another combinations of planes. That means already we have studied xy plane. Next we'll say what is yz plane. Next we'll say what is zx plane. Or we have studied about z is equal to constant plane. Next we'll say what is x is equal to constant plane and what is y is equal to constant plane. Okay, so let us proceed for another diagram. Consider another combination of planes. Earlier we have considered xy plane or z is equal to constant plane. Now here this time we consider another combination, there is yz plane. Okay, so consider this yz plane. So here consider this plane. For this plane, one side is consecutive with y coordinate, another side is consecutive with z coordinate. Okay, so this plane should be called as yz plane. Yz plane. But where this yz plane is located exactly, so that we can observe with respect to x-axis. Yeah. So you can observe here is, so this yz plane is exactly at the middle of the negative x and positive x. That is at origin at x is equal to 0. Okay. So this plane is also called as x is equal to 0 plane. X is equal to 0 plane. The plane which cuts the x-axis exactly at 0, or the plane which is located at x is equal to 0 is called as x is equal to 0 plane. Or we can say another explanation for this one. Let us consider any point here, any point on this plane. Okay, so this makes some length along y-axis, and it makes some length along z-axis. Okay, so we have a y coordinate and z coordinate. What about x? This plane is presented x is equal to 0, so coordinate x coordinate is 0. Okay, so like this, at every point of this plane, x coordinate is constant, which is equal to 0. That's why the plane is called as x is equal to 0 plane. Okay, so we define like this: x is equal to 0 plane means the plane on which at every point x coordinate is 0 is called as x is equal to 0 plane. Okay. Similarly, let us consider this plane. Move this plane some 4 units forward direction. Okay. So when we move this plane 4 units forward direction or along x-axis, okay. So then the plane looks like this. If you move this plane 4 units forward direction or along the x-axis, it cuts the x-axis at 4. Okay. Then if you observe any point on this plane, will be in the form of x coordinate is 4 and y and z changes according to location of this point. Okay. So the plane on which at every point x coordinate is 4 is called as x is equal to 4 plane. The plane which will touch the x-axis at 4 is called as x is equal to 4 plane. Okay. Similarly, consider this x is equal to 0 plane and move this plane some 5 units in the along negative x direction. Okay. If you move along negative x direction, then the plane will cut the negative x-axis at -5. Okay. So if you consider any point on this plane, will be in the form of -5 comma y comma z. The plane on which x coordinate is -5 at every point is called as a x is equal to -5 plane. Like this, we can define infinite number of parallel planes. Okay, x is equal to 20, x is equal to -40, x is equal to 100. Like this, we can define infinite number of planes. Okay, all these planes, all these set of planes combined are called x is equal to constant planes. X is equal to constant planes. Okay, and if you observe this one, all these x is equal to constant planes are parallel to this yz plane. All these planes are parallel to yz plane, and all these planes are perpendicular to this x-axis. Perpendicular to x-axis. Okay, and we need to know what is a differential surface element for this one. Okay, so differential surface element. Differential surface element. Yeah. Already we know that differential surface element represents differential area or area of the surface into direction of that surface.
Okay.
Okay. So now just consider any small surface or differential surface on this plane.
Yes.
Any small surface on this surface. Okay. So one side is along y-axis. So this differential length is dy. Another side is along z. So this differential length is dz. Okay. Then this total area or differential area of the surface is nothing but dy into dz. So the area of the surface is dy into dz. And what is the direction of the surface? Okay. So here this surface is showing x direction. One side is along x direction, or one side is facing the x direction, and this back side is facing negative x direction. Okay. So this is along positive x and negative x direction. Okay. So the direction is plus or minus ax cap. So the differential surface element ds bar is equal to plus or minus dy dz into ax cap is the differential surface element for x is equal to any x is equal to constant planes. Okay. Now we move for another combination of planes. Now consider another combination of planes. Here we have studied already what is a xy plane, yz plane and zx plane. Okay. Now we will see what is a zx planes. Yeah. So observe here. So I consider negative y-axis also. Negative y-axis also. Here consider this plane. Yeah. So for this plane, one side is along z-axis, another side is along x-axis. Okay. So this plane is with the combination of x coordinate and z coordinate called as xz plane. Xz plane. And you observe here where this plane is located exactly. This plane will cut the y-axis at the middle. So if you consider y and minus y-axis, exactly at the middle this plane is present. Okay. So we say that it is present at y is equal to 0. Okay. So this plane is called y is equal to 0 plane. Okay. Or you can observe any point on this plane. Consider any point on this plane. Okay. So this point makes some length along x-axis. So it will have x coordinate, and it makes some length along z-axis. So it will have a z coordinate. What about y? It is present at y is equal to 0. So any point on this plane will be in the form of x comma 0 comma z. Or we can say that every point on this plane will have y coordinate 0. That's why it is called as y is equal to 0 plane. Okay. So move this plane 5 units right side direction or towards y axis. Okay. So here when we move towards y axis 5 units, the plane will cut the y axis at 5. Okay. So it moves from 0 to 5. So this plane is called as y is equal to 5 plane. Or any point on this plane will be in the form of x comma 5 comma z. As the location of this point changes on this plane, okay, x and z changes, but y coordinate remains constant, that is 5. So it is called as y is equal to 5 plane. Okay. Similarly, so consider this y is equal to 0 plane, move this plane some 3 units left side direction, okay, along a minus y direction. So the plane will get the negative y axis at minus 3. So that's why this plane is called as y is equal to minus 3 plane, and any point on this plane will be in the form of x comma minus 3 comma z. So at every location on this plane, y coordinate is minus 3. That's why it is called as y is equal to minus 3 plane. Okay. So like this, how many planes are defined? we can define infinite such a planes, infinite parallel planes like this. Okay, all this set of planes are called as y is equal to constant planes. Y is equal to constant planes. Okay. Now, if you observe this one, what is y is equal to constant planes means all these planes are parallel to xz plane. These y is equal to constant planes are parallel to xz plane. And all these planes are perpendicular to y axis. Okay. So, perpendicular to y axis. Simply, the planes which are parallel to xz plane and perpendicular to y axis are called y is equal to constant planes. Okay. So, now we need to know what is the differential surface element here. Okay. Consider differential surface elements. ds bar. So, here you know the differential surface element is given by area of the surface into direction of the surface. Okay. So, consider any infinitesimally small or very small surface element on any one of these plane. Okay. Here for the surface, one side is along z axis, so differential length is dz. On another side is along x axis, so its length, the differential length is dx. So, what is the area of this plane or area of this differential surface? Dx into dz. Okay. So, area of this surface is dx dz. Now, so this area of the surface is facing which direction? So, here this area of the differential surface is facing z direction, sorry y direction, positive y direction a by cap, and another side of this area is facing negative y direction minus a by cap. Okay. So, we say that the surface direction or differential surface element direction is plus or minus a by cap. Okay. So, plus or minus a by cap. So, finally, differential surface element is given by plus or minus dx dz into a by cap. Yeah. So, like this we define the differential surface elements or planes. Yeah, here till now we have studied about planes. First one there is a z is equal to constant plane, next one x is equal to constant plane, now it is y is equal to constant planes. Okay. So, now I have a question here. So, here in 3-dimensional coordinate system, the planes are constructed with how many coordinates is the first question. Another one, the planes are represented with how many coordinates? Okay. So, construction of the plane and representation of the plane. Okay. So, here he said that all these planes can be written in the form of y is equal to constant plane. Okay. This is called as a representation of the planes. Representation of planes in 3-dimensional coordinate system. Okay. Example, in 3-dimensional coordinate system, planes can be called as x is equal to 2 plane and y is equal to 3 is a plane, z is equal to minus 5 is a plane, x is equal to 20 is a plane, y is equal to minus 40 is a plane. So, one coordinate constant is always represents plane in the 3-dimensional coordinate system. It may be plane or surface. Plane or surface. Okay. So, in 3-dimensional coordinate system, one coordinate constant is always represents plane or surface. Okay. But the planes or surface are constructed with the how many coordinates? 2 coordinates. Okay. One side is along x, another side is along z. Our surface or plane will have 2 dimensions. One dimension is with respect to x, another dimension is with respect to z. This represents construction of plane or surface. Plane or surface. Okay. I am going to say that in 3-dimensional coordinate system, that may be Cartesian or cylindrical or spherical coordinate system. in any three-dimensional coordinate system. So, one coordinate constant represents a planar surface, or planar surface is constructed with two coordinates or two dimensions. Okay. So, that is why it is called as a two-dimensional region. Planar surface is called as a two-dimensional region. Okay. So, this is about planes. So, I will give you overall view of these planes here. When planes are two-dimensional, I will write a differential surface element. If you see differential surface element, surface is constructed with two coordinates. Okay, that may be with x and y, or y and z, or with the z and x. Any surface is constructed with xy or yz or zx. Okay, what is the surface element? If surface is constructed with x and y, I will take plus or minus common. So, area is dx dy, direction is az cap, plus or minus is taken common. Or, what is the surface element if surface is constructed with y and z? Area is dy dz, direction is plus or minus ax cap. Or, the area of this surface element is dz dx and the direction is ay cap. So, like this we can write down any surface element that happens in the three-dimensional coordinate system, that is Cartesian coordinate system. Okay. So, simply surface may be constructed with xy or yz or zx and corresponding differential surface elements. Okay. So, this is about surface. So, next session, in the next lecture we will see what is the representation of lines. So, in Cartesian coordinate system we have studied about what is right-handed and left-handed coordinate system. Then we have studied about representation of planes or surface. Okay. So, next one is lines. Here consider, I will explain lines with the help of an example here. So, let me consider coordinate axis, Yeah. Here if you observe this one, here I have represented a line, example for line. Here x is equal to 3 and y is equal to 4. Two coordinates constant always represents a line or curve. Okay. So, here it may also be represented as a 3, 4, z. Okay. Here if you observe this one, x coordinate is 3. That means we need to consider 3 units on x axis. Okay. And y coordinate is 4. Y coordinate 4, consider 4 units on y axis. Okay. So, these two will coincide at a point. This is the point where x value is 3 and y value is 4. Okay. Now, what about z? Here z is not specified as a value, it is specified as a coordinate. Okay. General coordinate. So, z takes all the values from minus infinity to plus infinity. Okay. So, now let us take all the values of z. So, z is equal to minus infinity to z is equal to plus infinity. Okay. So, then it becomes a straight line if you take all the values of z passing through x3, y4. Okay. And this straight line is parallel to z axis. Okay. So, simply we say that 3, 4, z represents a straight line parallel to z axis. Okay. So, this is the straight line. Earlier when we have studied about surface or planes, we have studied what is the differential surface element. Similarly, here also we need to know what is the differential length element. Okay. So, here differential length element. Differential length element. Yeah. Here differential length element is denoted with the dl bar and it represents length into direction or differential length into direction. Okay. If you consider this straight line, on this straight line consider any differential length or a very small length. Okay. So, this length is parallel to z axis or z coordinate. So, this differential length is denoted with the dz. Okay. Is the differential length or small length. Okay. So this length it can be extended in which direction? This length can be increased towards z direction or towards negative z direction. Okay, so that means here the length is dz and the direction is plus or minus az cap. So differential length element is given by differential length is dz, direction is plus or minus az cap. Okay, so differential length element dl bar is plus or minus dz az cap. Okay, now observe this one. Here why do we need a length element means whenever you want to perform line integral of any vector dot dl bar. Okay, here you require to perform line integral you require differential length element. So this is the differential length element if you consider a line parallel to z axis. Okay, so this is the way how we are going to use the differential length element in line integral. Okay, similarly you just consider second example. Okay, just by seeing this example you tell me you can tell the line is parallel to which axis. Okay, so here it is x comma 4 comma 5. Okay, or y is equal to 4 and z is equal to 5. It is a straight line parallel to x axis passing through y is equal to 4 and z is equal to 5. This is the idea. Okay, so then let us sketch what is the straight line diagram. Yeah, consider coordinate axis and here y coordinate is 4. Consider 4 units on y axis and z coordinate is 5. Consider 5 units on z axis. Okay, so these two will have a intersecting point. So this is the intersecting point. This is the point at y 4 and z is equal to 5. Then what about x? X is a coordinate, takes all the values from minus infinity to plus infinity. Okay, so then take all the values of x from minus infinity to plus infinity. This is x is equal to plus infinity, x is equal to minus infinity. Okay, so this is the when you extend the values x is equal to minus infinity to plus infinity passing through y4 and z5, the line is parallel to x axis. Okay, this is a straight line parallel to x axis. And can you tell me what is the differential length element? Here the differential length or small length, this is the length parallel to x axis. Okay, so differential length is dx. And what is the direction? It may be extended towards negative x or towards positive x. So plus ax cap or minus ax cap. Okay, then differential length element is given by dl bar is equal to dx into plus or minus ax cap, or it is plus or minus dx into ax cap is the differential length element. Okay, here what we can observe here is, here earlier we have studied a representation of planes or surface. There one coordinate is equal to constant always represents a plane or surface in 3-dimensional coordinate system. Similarly, here our observation is when two coordinates are constant, it represents a line or curve. Okay, so for plane one coordinate is constant is a plane, when then two coordinates constant is a line. Okay, so let me tell you one more example here, another example. Consider a third example here. So here you can observe x coordinate is 3 and z coordinate is 5 and y takes all the values from minus infinity to plus infinity. So simply by observing this we can say that it is a straight line parallel to y axis and passing through x3 and z is 5. Okay, let me show you in the diagram. Consider coordinate axis x, y, z and horizon. Okay, so x coordinate is 3, so take 3 units on x axis, and z coordinate is 5, take 5 units on z axis. These two will have a intersecting point. This is the intersecting point where x value 3 and z is equal to 5. Okay, and take y value is from minus infinity to plus infinity. If you take all the values of y, that is from minus infinity to plus infinity, it becomes a straight line parallel to y-axis. So this is the straight line parallel to y-axis that is represented with the 3 comma y comma 5. Okay. So consider differential length element. So differential length, this differential length is parallel to y-axis. So differential length is dy and the directions are minus ay cap or plus ay cap. Okay. So differential length element is given by dy into plus or minus ay cap is the differential length element for the given example 3 comma y comma 5. Okay. So here, as already we discussed, let us consider an example here. In 3-dimensional coordinate system, when I write 3 comma y comma z, second one 3 comma 4 comma z, third one 3 comma 4 comma 5. Just observe these three. Among these three, which one represents point and which one is a line and which one is a plane? Okay. So in 3-dimensional coordinate system, it may be Cartesian or cylindrical or spherical. Okay. Here we can observe that when 3 coordinates are constant, okay, it represents a point. Point is represented with all the 3 coordinates are constant. Okay. When only 2 coordinates are constant, what is the meaning? X is equal to 3, y is equal to 4 and z takes all the values from minus infinity to plus infinity. So we call this one as a straight line parallel to z axis and passing through x3 and y4. Okay. So this is a line parallel to z axis. Parallel to z axis. Line parallel to z axis. Okay. Similarly, if you observe first one, here only one coordinate is constant. Okay. When only one coordinate is constant, it is called as a plane. Okay. So here x coordinate is 3. So x is equal to 3 here. So this is called as x is equal to 3 plane. This is called x is equal to 3 plane. Okay. Which is parallel to yz plane. Parallel to yz plane. And it is a perpendicular to x-axis. Perpendicular to x-axis. Okay. So this is the way how we can represent a point, line and also plane in any 3-dimensional coordinate system. Okay. Now let me finally conclude what is the differential length element, surface element and volume elements. Okay. So first consider differential length element. Differential length element. We know that length is a one-dimensional region. Length is a one-dimensional region. So length is constructed with one coordinate. Okay. Here in Cartesian coordinate system, length is constructed with either with x coordinate or with y coordinate or with z coordinate. Okay. And length element is given by, here I will take plus or minus common, that is negative direction and positive direction. Okay. Here x will produce a differential length dx and its direction is plus or minus ax cap, or y will produce a differential length dy and its direction is plus or minus ay cap, which is taken common, or z will produce a differential length dz into plus or minus az cap. Okay. So this is the complete differential length element. The meaning of this equation is that in Cartesian coordinate system, differential length may be due to x or due to y or due to z. Okay. So this is the differential length element we use when we perform line integral. When we want to evaluate line integral, this is the differential length element we need to substitute. Okay. So next one. Similarly, differential surface element. Differential surface element. You know that surface or plane is a two-dimensional region. So the surface is constructed with any combination of two coordinates. Okay. So then with x and y we can construct a surface, or with the combination of y and z a surface can be formed, or with the combination of z and x a surface can be formed. Okay. So then differential surface element ds bar is given by, you know, the differential surface element represents area of the surface into direction of the surface. Okay. So there will be two directions, one is in positive direction, another one is negative direction. Okay. So then what is the differential surface element with x and y? Its area is given by dx into dy is the area. Direction is in the remaining coordinate direction. Okay. Two coordinates will construct two sides of the surface or two dimensions of the surface. Remaining coordinate gives the direction of that surface. Okay. So the direction of the surface must be in plus or minus az, or the r operation is indicated with the plus and operation is represented with product. Okay. So y and z, a surface with y and z will have a differential surface element dy dz. Direction is remaining coordinate direction, there is a plus or minus ax cap, or surface element with z and x. Okay. Area is dz dx and direction is in remaining coordinate direction, there is dy cap. So like this we can write down the differential surface elements for surface xy or yz or zx. Okay. So this is useful when we perform surface integral of any vector dot ds bar. Okay. Here we are going to substitute proper or appropriate surface elements according to given problem. Okay. So next third one is differential volume element. Okay. Right here, differential volume element. We know that volume is a three-dimensional region. Okay. So the volume must be constructed with all the three coordinates. Okay. So there is volume must be constructed with x and y and z. Okay. And volume element is denoted with dv. Differential volume element is dv. Okay. Then what is the differential length due to x? dx. Differential length due to y? dy. Differential length due to z? dz. So product of all the three dimensions or three sides gives us volume element. Okay. So this is the differential volume element. So whenever we perform volume integral of any scalar into dv. Okay. So we are going to substitute volume element here. Okay. So now, so this is the way how we can write out differential length element, surface element and volume element, which are very useful when we perform the line integral, surface integral and volume integrals. Okay. But here an important observation is, so here length element, differential length element is a vector. Okay. And the differential surface element is also vector. Okay. But what about differential volume element? Differential volume element is a scalar. Okay. Here the reason is that the volume is always multidimensional. Any volume will have so many directions, so we cannot assign a particular direction for the volume. Okay. So it should be considered as a only magnitude. Okay. We cannot assign direction for this multi-directional volume element. For example, you consider a cube. Consider this cube. There is a cubical volume, I mean to say, it is a cubical volume. First, so you tell me this volume is facing which direction, or this volume is showing which direction. Okay. So you can say that the volume showing upward direction, downward direction, right side direction, left side direction, forward or front direction and backward direction. Okay. So now if you just observe this one, so this volume is a multi-directional. Okay. It has so many directions. Okay. So for which we cannot assign a particular direction here. So we measure it as a only magnitude. Okay. Similarly, If you consider volume of a sphere, spherical volume you consider. Okay. Now you tell me, it is not a circle, it is a volume. So is sphere, it is a sphere actually, spherical volume. Now can you tell me in which direction the volume is showing, or volume is facing which direction? Okay. You are going to say that the volume is facing all the directions or infinite directions. The volume shows infinite number of directions. Okay. So we cannot assign a direction for this volume because it is a multi-directional. Okay. That's why volume element will be considered as only magnitude here. Okay. So this is about differential length element, surface element and volume element, and this is about Cartesian coordinate system, important points in the Cartesian coordinate system. Okay. So next we will move to a cylindrical coordinate system, which is very important one.